We'll begin. Our presenters are here. Yeah, thanks again to everyone who is currently in this session of Localtalks. This is the third Localtalks event of the year. We've been hosting 4 of them per year every third month. So yeah, thank you for being with us. My name is Randy Karangizi and I work with Localworks, which is a design and build practice based in Kampala, Uganda. And this platform is really there to just be a space for conversations around green design in East Africa. And we've hosted a number of different topics and issues, and it's always been interesting to add to this knowledge that we're trying to share and build together. So the session that we have today is titled Counting Carbon, Quantifying Sustainable Construction. And we will be looking specifically at different carbon measurement tools that have been used in the construction industry for different purposes, and we will see kind of how they affect design and ultimately if they can promote more sustainable construction practices. We have 2 speakers with us that you can see. There is Joe Jack Williams there and also Tom Joseph Mukasa. And both of them will unpack this topic from different angles. They have different backgrounds. Joe is a partner and researcher at FCBStudios in London, which is an architectural practice. And Tom is a chartered quantity surveyor. He's the CEO of Pearl Engineering Company based in Uganda. And he is also a PhD fellow and lecturer at Makerere University. I think after both speakers will speak and then there will be a Q&A session. Which I think everyone is welcome to use the Q&A box in Teams, or you can also raise your hand and ask your question so that it can be interactive. Both options are welcome. I think I will give a slightly longer bio before each speaker speaks, and I'll keep it very summarized for everyone. And yes, I think that's kind of everything. This session is being recorded. We always record all the Localtalks sessions, and then afterwards we upload them to YouTube, our YouTube channel at Localworks. So you can go back and rewatch and still continue to ask questions if you like to. So here we go. Let's go. I think Joe will speak first. So Joe, as I've already said, I guess he works with FCBStudios and he leads the environmental research for the practice. He's a partner in the practice. He is a certified passive house consultant and has taught at a number of different universities in the UK, including Oxford Brookes, UCL, UWE, University of Bath, and London Met. And he's a part of a core research group within Architects Declare, CIBSE, and LETI, some acronyms. And he leads the development of FCBS Carbon, which is a free whole life carbon tool that he will tell us about. Exciting tool. So let me just mute all attendees. All right, so you are welcome, Joe, to go ahead, and then after you presented, we will unmute Tom to give his presentation as well. Thank you for joining.
Excellent. Thanks, Randy, and thanks for inviting me along to speak. It's nice. When we made this carbon tool back in, we released it back in November 2020. We didn't really envisage what would happen with it, so it's really nice to see it still kind of going and got legs. And it's nice to be talking about something that's so important. I'll share my screen. So for those of you who don't know, Phil and Clegg Bradley Studios we're an architectural practice, as Randy mentioned. Hang on, I've lost my mouse. There we go. Let me just move that out of the way, and then you can kind of all see my screen a bit better. So we're an architectural practice based in the UK. We do work internationally, so we're doing a bit of master planning work in Kigali at the minute, and we've worked sort of extensively around the world. And we specialise in sustainable design. We've been doing this for over 45 years. Peter Clegg, one of the founders of the practice, started thinking about sustainability back in the oil crisis of the 70s, which weirdly came back round again last year. I'm sure you all remember. So really kind of interesting how, you know, market forces drive it. But as a consequence, we've been thinking about carbon and energy for a long time. For us, embodied carbon is something we started to think about probably 2010, and we started to pick up, and over 2019 we started to build our own little tool, and that's kind of what I'm going to talk about today. So I'm going to give you a quick overview of carbon. So what is embodied carbon? Just a kind of really quick grounding. What I want you to get from this really is to understand how kind of simple it is in some ways. There's loads and loads of complexity that comes off it, and I know Tom's going to talk in a bit more detail about some of the ins and outs of it, and we can pick up those questions afterwards. I really like difficult questions, so feel free to ask them. I've obviously made my life difficult in the past doing this, but I think it's really interesting because the discussion that goes with these things is really quite useful. And I'll talk a bit about FCBS Carbon. Obviously, I'm going to talk about this tool. It's free. You can download it. It runs in Excel. You don't need any expensive software. It's fantastic for that kind of thing. I'll talk about the limitations, where it's good and where it's not so good, but hopefully it won't be too dry. There will be a demo of it at the end, which is me talking over a spreadsheet. I apologize. It will be a spreadsheet, but hopefully it'll be kind of fun. I've put lots of jokes in there, I'm sure. So what is embodied carbon? So really it's the gases associated with material. It's not just the CO2 or carbon that's in a material, but it's about the processes that come with making a material. We always express it in CO2e. The E means equivalent, so it could be CO2, but other gases, so methane's a classic one, refrigerants from air handling units or air conditioning, they're also global warming gases. So we convert them back into a kind of unit of CO2. So that's why you'll see this E dotted all the way through. So it's really important to think it's not just CO2. There's loads of other things that cause global warming, but that's what we talk about. And how do you kind of measure it? So these are my current go-to methodologies. So starting on the right, so Randy mentioned LETI, as it's pronounced, so L-E-T-I, LETI. For those of you who haven't come across LETI, there's a website, leti.uk. Loads of fantastic free advice, really intuitively written. It's written to get people to bring up that base level of knowledge. The Embodied Carbon Primer is great. It's quite long. It's about 100 pages, I think. But it's got some really nice little diagrams. There's lots of really good resources on LETI. If you're not familiar with them, have a little look. Although it's written for the UK market, lots of the ideas can still work sort of internationally. And in fact, it's been downloaded in over 120 countries, I think, last time we looked. Wild. Anyway, so that's on there. The one in the middle is the new RICS guide. Came out yesterday, hot off the press. This is a really comprehensive and useful guide. This is the one I point people to. I point to LETI first, and if they're really interested, then I point to this RICS guide in the middle. Again, it's free. It's really detailed. It's setting the kind of international standards, if you like, about how to think about whole life carbon. If you're really interested and like a dry read, there's a BSEN 15978 on the left, the standard that sort of underpins them all. I very rarely read it. It's not that interesting. It's not very intuitive. And in effect, it sets up the framework, which the other documents fill out far better. So yes, have a look at it, be aware of it, but I'd look at the other two first. There are loads of other good guides out there, but these are my kind of two go-to guides, if you like. So those are the kind of key. And what they all kind of say is the same thing. And one of the things I really want to start to sort of impress is this idea of a kind of constant language, so people understand that we assess buildings over different life cycle assessment stages. So these are the life cycle assessment stages in BSEN 15978. They are exactly the same in the LETI guide. They're exactly the same in the RICS guide that I showed. And they're exactly the same in nearly all the guides out there. There's a few differences, but we don't need to worry about those. But it allows us to have a common language to talk about the stage of a project. So on the left, we talk about the product manufacturing emissions. So this is the emissions of taking, a product from a hole in the ground or a forest or wherever those raw materials come from, transporting them to a factory and then turning them into, a useful material. So that could be multiple trips. If you think about aluminium, it might be mined in Brazil and then shipped around South America, and then shipped to China, and then shipped back to Europe, and then shipped elsewhere. There could be multiple stages to turn it into some useful material. So that's where the most of the embodied carbon is. This is the kind of key stage. Then we have this next bit where we start to include the construction phase. So we've got the product at the end of A3, so A1 to A3, that's the product stage. A1 to A5, we call that the upfront stage. So that starts to include the product being transported to the site, but also how you build it. It's not just about the energy used for building stuff, it's also about how much you waste. You know, if you think about offcuts of timber, where do they go? You know, do they end up in landfill, or do they get reused on site somehow? Or is there any offcuts? Have you designed it so it's all just fit standard sheet sizes? So all of those kind of bits get wrapped up there. Then we have this next stage, which goes all the way up to B5. So we take all of that upfront carbon, and we go from A1 to A5, and then B1 to B5. So that's how the building gets used. So is it maintained? Think about we define the length of a building as 60 years, just for standard comparisons. It's not necessarily going to last 60 years. It might last longer, might last less long. But these have got those kind of simple bits in it. So it's about how it's used, how it's maintained, how it's repaired, how many times it's replaced. So that could be quite a high carbon content. If you think about, you know, maybe it's a door. Doors get used a lot. They might not last as 60 years. They might only last 10 years, 15 years, 20 years. So there might be a few doors. Things like air handling units or air conditioning units, they might last 15 years, and they'll be, you know, replaced every 15 years. So they can be quite high. And then refurbishment's about how you refurbish the building. It's another kind of big bit. And then you've got the end of life at the end of it. So these kind of C modules, we call them. So C1, C2, C3, C4. And that's really how you take your building down. How do you process all of that kind of waste? And then what happens to it? You know, is it incinerated, or does it just end up in a hole in the ground? So really useful. What I haven't mentioned in the middle, there's B6 and B7. Those are operational energy. I'm not going to talk about operational energy today. And operational water use, obviously, they've got a carbon impact as well. So very important to think about. And the other one here on the end, sorry, I haven't shown you, is module D. So you might hear a lot of talk about circular economy. This is where module D is. So it's about benefits outside the boundary of the building. So if you think our building ends at the end of C4, goes A1 to C4, if our materials are still reusable at the end of its life in module D, that's where it's really kind of beneficial. So it'd be really useful just to keep these kind of ideas in your head. Hopefully, as this becomes more prevalent, you'll start to hear these terms a bit more. It's useful just to kind of be aware of them. You don't necessarily need to know them inside and out, but just know, like, if it's about A, it's about before the building. If it's module B, that's during the building. If it's module C or D, it's after the building. So get that kind of idea going. It's quite useful. And it's really simple to calculate. So this is the calculation methodology. You basically take the quantity of material you've got. Maybe that's from a helpful quantity surveyor like Tom, or maybe it's you have a BIM model or some sort of 3D model, or maybe it's just a simple estimate. You know, there's lots of ways you can do these kind of things. So, and it could just be you've got a little layout plan, you just measure it all off, or maybe you've talked to a local contractor, they've got an idea of it. So there's loads of ways to get the quantity of material. That could be mass, or it could be volume. And then the next thing you do is you take the emissions per unit. So you don't have to calculate this. You just have to take the data from elsewhere. So the classic one is an environmental product declaration. Some bits of software have them already built into it. There's another one called ICE database. I'll show you all of these as well in a second. So what you need to do, multiply them together, job done. You've got the resultant figures, right? So it's super easy. All you need to have is those two bits of data. Now finding them's the tricky bit. I'll show you just quickly how to do the emissions per unit. So, oops, hang on. Oops, if I'm on the right screen. So where are you going to get the sources of data? So it can be kind of nerve-wracking to think that you might have to work them all out yourself. We very rarely have to. You can do that, but that's a long, long day for everybody. What I'd recommend is start to look for existing sources of data out there. So this is from the University of Bath. It's the Inventory of Carbon and Energy. It's free. You can go to that website, you can download it. Their averages, now their averages based on sort of North European products. Now, interestingly, we don't think they'll change much for most materials, depending where you are. In fact, they're just as relevant in, say, Uganda as they probably are in Australia or South America or North America. North America can be slightly different. They have slightly different energy factors. We all have slightly different energy factors, but broadly speaking, the trends you'll see in the materials will be largely correct. So this is a really good resource. It'll tell you what the kilograms of CO2 per kilogram of carbon is, or kilogram of material. So this is for glazing, you can see. It'll tell you the DQI on the end, which is the data quality indicator. So it'll tell you whether it's a trustworthy number, also really important to know. So you can start to get an idea of, there's a good data set. So you can already think, okay, I've got this much glass, I've got these figures, multiply them together. You can very quickly work out the embodied carbon of your glazing. Really, really simple. We can probably estimate how many square meters of glass we've got. If you start to get a bit further down the line, maybe it doesn't have the material in here, it doesn't have all the materials in this database, you might want to start to think about looking for an environmental product declaration. Now, environmental product declarations can be quite complicated beasts. There's lots of data in there. These are two of the key places I start to look. So there's EnvironDec, there's Green Book Live. There's also other ones out there. There's EC3, which is a US one and is free. France have a fantastic one. I forget what it's called. I think it's ines.fr. However, these databases are fine. What I generally do is you Google. I just put in the product name and EPD, and it's far better at finding them than these websites. So that's my start point. Google it if you can find it. Great. And they'll give you a bit of data on it, and they'll tell you what the embodied carbon is, and they'll tell you a bit more about where your products come from. They'll also tell you things like how much water was used and how much land was used for it, and loads of really interesting things if you want to get down that kind of rabbit warren. I very rarely look at the rest of them. I do occasionally, but there's loads of data. What I would say is if you're struggling to read an EPD, they are quite tricky. There's a fantastic guide from the iStructE, so Institute of Structural Engineers in the UK, for free about how to read an EPD. It's really good, really intuitive. I'll just take you through it. There's a lot of technical language in there, which can be a bit daunting. So definitely have a look at it. So that's great. So we've got the data. So all we need to do is work out the material quantities, right? So not so simple. I sort of glossed over it and said, you can get it from a model or a CAD drawing or whatever else you've got. Well, that's fine if you've got one, but this is really where FCBS Carbon comes in. Some of the biggest savings we can make in carbon, bear in mind we made a carbon tool not to record carbon, but to help people reduce carbon. And I think it's a really important thing. It's very important to understand where your carbon emissions are, but you start to need to reflect on that and then think about how you can reduce it. So we look at the air carbon emissions from our buildings, and then we think, okay, well, our next project will be better. FCBS Carbon, however, is built slightly differently. So really, this is how many projects we had in FCBStudios. This is a few years back. So at the bottom is the RIBA stages. So stage 0 is very much briefing. Stage 1 is about understanding how much space is needed. And stage 2 is about kind of getting a design locked in. Stage 3, is technical design. Stage 4 is getting that even more technical. And stage 5, we're on site building it. So it's useful just to kind of see where we are at those different stages. But what we're really saying is, as we, if I want to make low carbon changes to a project, a stage 0, 1, and 2, those early stages where it's just a kind of, it might be a simple box we've drawn, a simple model, it's really easy to make those changes. At stage 3 and stage 4 gets very, very difficult. And stage 5, they're building it on site. Nobody wants me to set up on site and tell them to change the type of material they're using, or maybe we should change the layout plan. I'd be laughed off site, probably quite rightly. So really what we're looking at is those kind of first few stages. That's when we can make changes cheaply and quickly. There's no impact on program necessarily. There's no impact on sort of contractors and costs. Things are just within the design team. That's fantastic. But if you think about how long these things can take, so if you imagine we had 2 simple designs, and we had to work out which one was best. Now, we never have 2 simple designs in FCB. I looked at a project the other day, we had 30 different designs for the same project. It happens. I'm sure many, if there's any architects on board, you'll recognize that. So what we have is, just as an example, 2 different massings. We might have 3 different ways of making a structure, 3 different facade materials, 3 different floor materials, and a couple of different approaches to glazing. So that would give us 108 design iterations. Now, that's a lot of iterations. That's a lot of quantities to find. And to give you an idea, on a recent project we had, it was full BIM Revit model, so full 3D model. Everything was tagged with the materials. We used one-click LCA, which is a kind of online software, and you can export quantities in. It still took us nearly 6 days to analyze the whole building, and we had an amazing amount of data for it. So if we were to do it, maybe we've got a bit quicker, maybe we could do it in 5 days. 108 design iterations would take us 2 years of work just to work out what's the best design, right? It is just too long. So this is really where FCBS Carbon came in. So although it does do embodied carbon, really it's about creating a bill of materials and a quantity of materials that we can start to use in that calculation I showed. So that's really where it sits, and it helps us to understand the impact of our decisions. So it's not a real building, it's a kind of notional building using algorithms to describe it. And then we have kind of standard construction build-ups we apply to it. So when we say it's a brick wall in the UK, it's not just a brick wall, it's a brick wall with blockwork behind it, or it's a brick wall with a steel framing system behind it. We build all of that in, so you don't have to worry about calculating it. And it's really about helping us kind of record it. It's really helping us estimate it. It's about understanding how our buildings emit carbon. So I spend all day talking about carbon. Lots of people don't. More for them. They should get on the ride. It's all good fun. But getting those ideas in, and part of the design intuition, it takes time. And what I wanted this to be is a live design tool, so people can design around it, build it quickly, get a rough answer, make a change, see if it's the direction is going in the right direction. Is it lower carbon or is it higher carbon? And by how much? Is it 2 kilograms or is it 100 kilograms? It's very difficult to predict. So this is really what the tool's done, and it's done in Excel. So as I said, it's free to download. You don't need to have an expensive Autodesk license to make it work, or a MicroStation license. You just need Excel. And in fact, we do it on early stages in projects. We use it with Google Earth. I can quickly model up an existing building, for instance, and see roughly what the carbon emissions would be from that building if we were to replace it like for like. Or we could look at other options, what happens if we replace the facade or something like this. So really super basic. And that's the kind of approach. It's not about being accurate, it's about getting the right kind of answers and heading towards more accuracy. So this is what's included. So you've seen all this before. This is all looking familiar. We do all of the life cycle modules. We include energy use in it. I'll show you that, but I won't talk too much about it. But really what it's actually doing is we take the first bit, A1 to A3, and then we, I mentioned earlier that that's the most important section in many ways. And then we use percentage uplifts on the rest of it. So we know that 80% of the carbon emissions are in A1 to A3. That's where the things are made. And the rest of them tend to be fairly minor. Now, FCBS Carbon can be accurate. We did a study the other day, showed it was within 10%, based on modeling the building for half an hour compared to a 5-day model, which is fantastic. Some buildings will be better, some buildings will be worse. It's internally consistent. So whatever changes you make, you should see them kind of go up and down roughly in those kind of proportions, right? So just bear that in mind. It's never going to be perfect. Tom, I know, is going to show you a far more accurate kind of analysis. So, bear that in mind. It's in Excel, so there's there's a color scheme for it. Things that are in yellow are inputs. Things that are in a dark blue gray are calculators, so you don't need to worry about those. There's only 3 input pages. That's where you spend most of your time. Bit on project details, energy, and then the embodied carbon page. And there's a bit on the output, so an overview and a kind of detailed one. So I spend most of my time in the detailed one because I'm a geek, a self-described geek, love it. But also, think about the overview. The overview one can be used for reports and helping other people along. So I'll show you all those as well. So this is the first page. I don't expect you to be able to read this. I'll show you the spreadsheet in a bit, and we can zoom in and pick some of these bits up. This space, if you want to put any sustainability aspirations, what I would say is there's a few bits on this page that need to have input in there. They've got a little red star. It's probably quite difficult to see. There's a little red star against these four. If you don't put them in, the spreadsheet will break and it'll be really difficult to find out why it's not working. So make sure you work through it from the start all the way through. So fill in those four bits, then move on to the next bit, and then move on to the next bit. And the one that's public release has only got, I think, 3 sectors in there. So housing, offices, and education. If you think of offices as just being non-domestic, that's probably the way to do it. So if it doesn't fit into any of those sectors, probably just pick offices and you'll be fine. There's a bit on operational energy, so you can put it in. Now, we use UK carbon factors in this. It was built in the UK market. So you can put this in. It probably won't accurately reflect the energy market in Uganda. So just bear that in mind. It might help just give you an idea of where your energy use is. But again, the benchmarks are based on UK benchmarks. So perhaps not the most useful bit. But we can talk about that at the end if people have questions. And this is the kind of, I'm going to call it exciting bit. Let's call it exciting bit. So this is, you can see the bits in yellow you have to fill in, the bits in blue you don't. We've got a kind of live graph so you can see where your proportion's going and what's changing. This bit in the top left is the key bit. There's 7 input parameters, and these 7 input parameters describe most of the building, the kind of physicality of it. So it's the perimeter, it's the footprint, it's the width, it's floor-to-floor height, stories above ground, stories below ground, and glazing ratio. So just to note, the width is just a kind of arbitrary dimension. So pick a narrow bit through it, put the width in there. That'll help just to understand what the grid could be. The floor-to-floor height should be the total height of the building divided by the number of stories above ground. So just pick those in. And if you don't know one, guess. Glazing ratio, maybe you don't know how much glass is going to be in the building. Pick a number. You can build up the rest of the building and then change it. It's really quick to change. We can see that as well. So then this is probably where you'll spend most of your time. So here, this will come pre-populated with every building aspects, all of substructure, superstructure, floors, roof, walls, all this kind of stuff. Then there's building elements within them, and then there's a curated list of common materials. Now we've got some interesting materials in there that might be useful in Uganda. Some are going to be UK based. Hopefully, that'll give you a bit of a flavour. We can choose whether it's existing. Are you reusing bits and you get benefits for that? You can use the adjustment factor. The adjustment factor is there, and I'll show you how to use that for kind of making it work a bit better. Overriding some of our guesses. And here's where you say how long you think your building element's going to last. This is based purely on your intuition. There are tables out there. I know RICS have tables, but this will help guide you towards how many replacement cycles there'll be over that 60 years. And just to note, each of those kind of materials will have it's not just a simple material, it's a whole build-up that makes that material work. And we pack those out with kind of FCB knowledge, if you like. I'll skip over that. And this is the main outputs. So this is output 3. So in the top left, you've got some operational energy bits. Top right, you've got embodied carbon, and you can see it's these bars at the top. That's against the RIBA 2030 challenges. So it'd be interesting to see how you compare. Whole life carbon, so if you take the energy and the carbon and you put them together, how does that fit? And then in the bottom right, quite often we get asked, what is that amount of carbon? What does it actually mean? It's quite a complicated thing. So we've converted carbon into areas of forest, so we've converted them into hectares, and it just gives you an idea about how much forest you really need to offset your building. So it's really quite an interesting thing to see. Quite often we get clients asking if I put a tree on my site, will it help? The answer is yes, it will help. Trees are always fantastic, but you need a forest to offset it. It's pretty much always the answer for us. So you can see, I won't take you through all these bits. I'll show you live. It's a bit more interesting. This is the detail output. So the top left here, this gives the breakdowns against those life cycle assessment modules, which I showed earlier. You can see here, it's got the biogenic bit as well, wherever my mouse has gone. I've lost it. Here you go. It's biogenic, so things, the carbon that's contained within it, energy, and then your module benefits. These are kind of reporting figures, so this is what you do if you're reporting against a standard. And then the one on the bottom left here just tells you how that carbon is going to be emitted over the life of that building, the red line being a kind of worst case and the green being a best case. So you can see it's going to be somewhere between it. So I've got kind of 4-ish minutes left, 4 or 5 minutes, but I'll just quickly show you how it looks. So bear with me. So And I'm going to open up a couple in the background as well while I think about this, as I close them down. So this here is the first page. I'm just going to hide that away. And you can see that these are the 4 bits we need to put in. Now, I've put in a dummy office. It's kind of fine. It could be any kind of building. This is our internal one, so it's got, oh no, it's got just limited number of sectors in. So we think it's going to be finished in 2024. We think it's an office building. We think the gross internal area, then this is all floors, not just one floor, will be 5,600. And I did this one apparently last year, probably because I've been adapting and copying it for years. I put in some energy data. Now, I didn't know what the energy data was, so I just guessed 110. We got some figures in here. Now, I'd recommend you think about how much energy it will use. Maybe it's an existing building, or it's going to be a new building, but they're moving from an existing building. Ask. Just to note, it's in kilowatt hours per meter squared of the year per year. So that's again in meters squared in GIA. So it's always talking about gross internal area. And then on to the good stuff. So this is I pre-filled in some of this. I mentioned here these are my kind of standard materials. So this is my standard dimensions. These are the key things to get right. Now, the most important thing is don't spend hours doing this. Put in a good estimate of the data that you think is reasonable. If you're spending hours measuring things, you're taking too long. Typically, so I can do this in like half an hour. Of course I can, it's my tool. Most people, when they first use it, they probably take 2 hours tops. If you're spending longer than 2 hours, you really probably spending too much time measuring things and being too accurate. So it really is about getting data in and then iterating over it and sort of improving. Just a note here, when this is number of stories ground and above, so if it's just a 1-story building, that would just be 1. And you can see I put in a glazing ratio here. So all you have to do, this will come pre-populated with all these kind of aspects in there. So all we need to do is just pick the materials so they're all in drop-down lists. So we'll make a piled building, why not? And we can start to go through and just pull these through. Now, I'm sure this is what you'd all love to see is me filling in a spreadsheet, but let's not bother. Let's go to one I've pre-done. Here you go. So you can see I've filled in all of these. And what I've got here is I've got, oh, I changed it to glulam. Let's just put that back to concrete. So I filled in all the ones that we need to fill in. I mentioned here about the adjustment factor. So we can use this to try and make our numbers more accurate. So if you scroll over to the right, you can see over here, I've assumed that my slab thickness would be 150 mil thick slab. So I think that might be a bit small. So I think for here, so I've put in 200%, so it's going to be twice as thick. I've also, let's pop that back to new. I've clearly been tinkering with this. I've also got 3 different lines about the floor. So I've got a raised access floor throughout all of the building. And then I've got 70% of it would be carpet and 30% would be vinyl. So we can start to add that in. And I put some sort of bits and pieces in there just to show how it kind of looks. And we can start to see very quickly, this is the breakdown of my project, and this is where we are. So I'm emitting 917 kilograms of CO2 per meter squared. If I go to my second page, my third output page, sorry, you can kind of see all these different aspects. You can see very quickly on here where a lot of the carbon's coming from. And services tends to be very high. You can see substructure and superstructure quite high here. Upper floors, this pink one here, again, quite a lot. And if we go into our kind of output graphics here, so this is the fun stuff for me at least, we can see 581 kilograms of CO2 per meter squared is emitted before the building's even used. Quite a staggering amount. These are your replacement cycles, so all those things getting replaced over the life of the building. This here is your energy. You can see those little replacement cycles happening here. Pop, 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 pop. So once we've got it built up, we can start to make changes to it. So for instance, you remember I said about the glazing ratio. If you don't know what the glazing ratio is, so if you look at this, it's 917. If I change this now to 50%, say, we can have a look, see if it makes much of a difference. It went up by 1, so don't sweat it, it's not that important. And you can start to think about, what if you don't have a basement and you make it 7 stories tall instead? We can go back over here and you can see it drop down to 800, I think that's 84. And you can start to change materials. So maybe you want to change the materials. So we do have some the materials in here. Let's have a little look for external walls. Maybe you want to choose. So I put some really low carbon ones in here this morning. So I put a rammed earth wall in. I'm not sure you could do a 7-story rammed earth wall, but what will happen? You can see it comes down quite a bit. And it makes a lot of sense when we start to look at this. You can see that the embodied carbon is dictated by the surfaces. So maybe I could change the surfaces from medium to low. And we can go up here again. And we can see we're starting to make those improvements. So that was a very much a whistle-stop tour of FCBS Carbon. I'm going to stop sharing. We can come back and have a look at it if there's Q&As, particular Q&As. What I would say is I'll put the location to download it from in the chat, and then you can all feel free to download it, have a tinker with it. Let me know if there's things you think are missing. Let me know if things are good or bad. It's all still under development. But with that, I'll hand back to Randy, who's going to introduce Tom. Thanks all.
Yes. Thank you, Joe, for that presentation. I think it was really interesting in the end to see it coming to life. And I'm sure we can go into it in further detail after this next presentation. So I'm just very quickly, I'm going to introduce Tom, as I did with Joe. Tom is a Ugandan construction professional with extensive experience in both academia and industry. He is a registered quantity surveyor and CEO of Pearl Engineering Company Limited. He is also a fellow at PhD fellow at Makerere University and a part-time assistant lecturer there in the university's Department of Construction Economics and Management. And he has his competencies encompass a wide range of skills, including project management and commercial management and various other things that he does. So thank you, Tom, for joining us today, and we look forward to hearing from you as well. Yeah.
Thank you, Randy, for the wonderful introduction. I must say that I'm impressed by Joe's presentation. I think he has done a very good job. I'm going to be the opposite, but I'm going to start from scratch, and I hope we should be able to catch up and be able to use the tool that is being offered by Joe, as long as we understand the basics. I'm going to share my screen, this screen. So I don't see myself, but I hope you can see me. I am going to tell you a little bit about the background of why measuring carbon has become very important or very critical for the construction industry. And I'm going to talk about another, I will call it a tool, but it's not a tool in the sense of Joe's presentation, but it's a set of processes that you can use or standards that you can use to present carbon measurements. So that is what I'm going to mainly talk about. And my motivation is to encourage most of us in Uganda to pick interest in measuring carbon, because there's a lot of pressure, external pressure that is coming from investors and other people, other stakeholders. And therefore, we need to prove that we are doing our things sustainably. Of course, there's the scientific aspects, which we don't want to face. You know what is going on around the world right now, and they're claiming that it's because of our activities. So with that, let me get into my presentation. So I've titled it Embracing a Greener Future. So the thing I'm going to be talking about is called ICMS 3 and carbon measurement in the construction industry. So let me get there. But before I get there, I picked some interest from Joe, contextualizing carbon. And last month I was having a presentation in Zanzibar, And I also tried to do that. I picked a lot of this from Institution of Structural Engineers. So I tried to compute how much carbon I was giving out in my travel. So I had moved from Entebbe to Zanzibar, and there was a carbon calculator which is also free online. Most of these tools are actually free. I don't know why. So I got something like 320 kilograms of carbon dioxide emissions for that one trip. Then another comparison is if we stop eating a lot of meat and dairy products, they claim that we can cut out about 2,000 kilograms of carbon dioxide per year. That is 2 tons. Another comparison is that if we stop driving our cars to work, I don't know what distances, but they say we can save about 3 tons of carbon dioxide per year. But the shocking thing was here at the bottom, that if we manage our designs well, these were structural engineers, and they were saying that if they can do a 20% structure, saves 20% structural embodied carbon reduction in their designs, they are going to save 200 tons of carbon dioxide per year. So you can see that what we do has a lot of significance compared to most of our other frivolous activities. Of course, we are so many, but you can see that just on one project, you have a lot of capacity to influence the carbon dioxide emissions you give out just by adjusting your design. And that is why it is important to do some calculation at the beginning and as you move with your projects. So that is the background. Otherwise, let me try to dive into this and try to move a little bit faster. I'm happy that Joe has actually talked about most of the things that I had planned to give us background or to make us understand. So I'll not spend a lot of time, but I'm going to start with the motivation. And the motivation is basically the reason why we are trying to manage carbon. And this comes from the history of climate change. So I have a slide on that, and also to try to see that we understand it, because personally, probably 4 years ago, I wasn't interested. But when these standards started coming up, I picked interest and I found it interesting. So probably most of us are like me 4 years ago. So where do we start from? So it's a global challenge right now, and it is coming out of our very many activities, economic, social, environmental challenges. So what has been happening is that we've been setting targets, and the key targets I can pick here are the 2015 milestones we set. That is the Agenda 2030 of the 17 SDGs, and then the Paris Climate Agreement. They all came out in 2015. However, this story starts around 1972, where people got concerned about our environment. And from then on, they started going into agreements and protocols. But the word sustainability came up, was popularized by a prime minister from Norway, and it was during it's called the Brundtland Commission of 1987. That is where they started the definition of sustainable development, of trying to cater for the future as we cater for ourselves. Then from there, they've been having a lot of agreements and not fulfilling them. At the moment, we are halfway the SDGs and people are in New York, but again, you can see that there's no agreement. The Paris Agreement also came into force, but again, it is like it's not a mandatory to follow the commitments. So those are the challenges we are facing. We set targets and we are not meeting them. So that is the background, but the scientists are telling us that the Earth is heating up. And why is it heating up? It is because of greenhouse gases. And what are these greenhouse gases? We all talk about carbon, but it's not only carbon. And how does this happen? So how this happens is that the sun comes to us and some of the heat is reflected back, and some is trapped to keep us alive. But with our increase in activities, we are having a lot of heat in the atmosphere, and therefore a lot of heat is being trapped. And once it is once we get a lot of trapped heat in the air, the Earth's surface is overheating, and it is causing a lot of problems, as you can see. But I'm not going to go into the science of how that is happening, but that is how it comes about. So it's about global warming, and therefore we have these four mainly global greenhouse gases, mainly carbon dioxide, which is the biggest, followed by methane, I think, methane. And then we have nitrous oxide, and then we have the fluorocarbons, the F gases. And these are the summaries of some of the activities that are bringing this up. Construction is obviously hidden under energy, but it is contributing, they say, about 40% of this. So I've tried to put a summary of these greenhouse gases, and we use carbon as the SI unit, but it's not only carbon dioxide that is out there. We have these other gases, and we always convert them to a global warming potential over 100 years. And you can see these are actually heavier in damage than carbon dioxide. So you can see methane is between 25 to 36 times more than carbon dioxide. Nitrous oxide is 265 to almost 300. The sulfur hexafluorides and all those are the things which are used in refrigerants are terrible, although they are not so much. So that is the context. And these are some of the effects of the global warming that we are faced with, from greenhouse gas emissions, the precipitation, the natural disasters, the rising sea levels, and the loss of biodiversity. Okay? Then that falls in these agreements that we are making and trying to curb the temperatures from not rising beyond 1.5 degrees to they say the pre-industrial temperatures. So, however, we need to contextualize this, that there has been an exponential rise of greenhouse gas emissions starting from the Industrial Revolution, and it has become too much, as you can see. From 1950 to the current, it has become too exponential, and these are the biggest emitters of carbon. Let me use carbon. And you can see there that China, basically it's the developed world that is having the biggest contribution. And therefore, a lot of effort has to be put in place by these people, including ourselves, but the majority of the efforts should come from them to bring this down. Okay, so for Uganda, I can say from the calculator I used, it's one of the lowest per capita. We are still enjoying one of the lowest average carbon footprints on the world. It is about 0.1.4 tons of carbon dioxide per person, compared to the global average of 4.79 tons. So that's a good thing, but we should not make the same mistakes as the mistakes that were made by the West. However, we have challenges in developing countries, socioeconomic factors. We need to improve our energy distribution, our availability of the energy. We need to build more houses because we have a shortage, and all this is going to require a lot of carbon emissions. So we are caught in a trap, and the only way at the moment we have to do is to see that the greenhouse gas movements, the green movement, the people who are promoting efficient energy and using low carbon technologies can bail us out. At the moment, I think it's too expensive, but there are a lot of other proposals that have been suggested, but I'm not going to talk about them. So the challenge we have is that we still need the energy, and therefore we need to start counting our emissions and be able to manage whatever we have as we move into the future. So that is the background. The second part is the tool or the proposal. This is a standard that has been promoted since 2017. It is called the International Cost Management Standard. It measures both the cost of construction and now it has introduced a section on carbon measurement. So it's a reporting standard. It's not a measurement standard. And the dream is to have a uniform or a consistent way of reporting these aspects of all our projects. So I believe it is an answer that we can all start following as a uniform format. And I also believe that Joe can actually do a little bit of adaptation on his tool to align it to this standard. And then also we will be able to enjoy his tool and as well as follow his standard. So this is what I'm proposing. So what is ICMS 3? So it's a global sustainability standard, pioneering global standards for harmonizing sustainable construction practices. So it goes beyond the finances, where it focuses on cost management. It also addresses a critical sustainability aspect, which is carbon measurement. It is a standardized framework developed through international collaboration, and it provides a framework for reporting both costs and carbon emissions in construction. Okay, it combines economic and environmental metrics for uninformed and long-term decision making. So it's an opportunity for us because it will create a common language for all of us as stakeholders to enable consistent project comparisons, both financially and environmentally. Okay, so by measuring carbon emissions, our decision makers will be able to understand the true environmental impacts of their construction. It's a universal carbon measurement tool, and therefore anyone can use it, and it's free of charge as well. So that is it. So as I told you, I have some interest in teaching or sharing knowledge. So I see that as an avenue that I can spread and make many people be able to adopt some of these things. So this is something we are promoting at our department when we are discussing quantity surveying principles, and this is going to become a very critical part of the course. So, and the message is that we need to shift our culture from looking at only immediate finances, but also looking at the future. So, if we all have a capacity to do this, we believe that we shall be making better designs which are sustainable. So that is the reason that I am actually trying to participate here. I'm supporting someone whom you know that he's too much into this research, called Dr. Nathan. He is even a co-author of this standard. So that is what I believe in. So how does the standard or the framework look like? So this cost management reporting standards has tried to amalgamate all the construction industry subsectors into one reporting framework, starting with buildings and adding on all the civil engineering and infrastructure works, as you can see. So they are all defined in this framework under projects and sub-projects. Then under categories, these are the stages of construction, from acquisition to construction to renewal to operation. So this is like whole life cycle accounting. So they have called them categories. And there you are doing both costs and carbon emissions. And then the group elements are really what we call the groups are what we normally call the elements, okay? And the subgroups are those other subsections under the various elements. And these are left to the locals to use your local standards of measurement, but you can be able to map to the framework. And that's what I'll be trying to do somewhere in the presentation, okay? So all these projects are there, from buildings to bridges to roads and these are their codes. So it is something for all of us. It's not only for the quantity surveyors, it is for all of us. Now look at the way they have arranged it under the categories. This is an acronym called ACROM, and that is life cycle: acquisition, construction, renewal, operation, maintenance, end of life. So those of you who are used to life cycle costing, this is very familiar. So look at the groups. These are almost like the elements. When you look at construction, we start with demolition and site preparation. Then we go to the substructure. They've dropped the word super because it was not universal, because outside the Commonwealth and Australia and Canada, you find that they don't use that language like in the US and in China and Japan. So they now use it as a structure. Then the finishes and all those non-structure works have their own group. Then you go to the services. Then you get to underground and surface drainage, then external works. So these are more or less like the elements we are used to. And then all these other operational subsections are also there. But the greens are the ones where you are supposed to measure carbon. The others are deemed to be negligible, to have little contribution, and therefore you are not required to do that. We have also tried to use Joe's approach to map our presentation to the existing framework for carbon measurement. So these are the stages that you've been hearing about, starting with A's, going to the B's and the C's and to the D's. Okay, so we all know that the early embodied carbon is normally in under A, but operational and maintenance coming under B, then end of life is in C, and then recycling and circular economy come under D. I don't have to say this. Joe helped me and explained this. So just have to pick interest. I don't have to define these definitions, but I provided them for anyone who is a novice, not to get intimidated. So you can always look at some of these definitions. We know that carbon is our SI unit. Then these are the stages. So the product stage is A1 to A3. Then the construction stage is A4 to A5. And mainly that is the critical stage of construction, where we have a lot of influence on the carbon emissions. Okay, so I'll concentrate on those first 5 stages. But we have the operational and in use, the maintenance, the end of life, and then module D. Good enough, Joe has helped explain all that. So when it gets to this standard, it has a section called carbon emissions. And we always have to start with defining project attributes and values. So you have to state the carbon emission measurements you are going to do, the boundaries of the carbon reporting, the percentage of carbon emissions based on the actual quantities, as opposed to forecasts, the name of the carbon tools you are going to use. There are so many as you've heard. The name of the certified carbon assessment process you are going to use, the main sources of material quantities for your assessment, and the emission factors and the pricing method. Then you can also talk about the energy sources. You know that some people use fossil fuels a lot. Others use a mixture. Some of us use hydroelectric a lot. So you have to state, and all those have an effect on the carbon emissions. So that is the first point you do. I've also provided links to the carbon factor databases that Joe was talking about. The most famous one is from Joe's university. Thank you for that effort that you did some years ago. And of course, it is accompanied by the ICE database, but they seem to be in a partnership. So we always go to the ICE database, which was jointly developed by Bath University and other people in the UK. So it's the one that has a lot of information, which is universal or global, but even all these others are good sources of information. So in your free time, you can go and look at them. Joe comforted us that we can use those sources reliably, even when you are in Uganda, because you'll notice that we seem not to have a database for Africa. I don't know whether we don't have any peculiarities from these other areas, but I would think that we should do something about it, at least to check whether our information tallies with what these other databases are giving us. Okay, so that is the second part, which talks about the standard. The third part is mainly to encourage people to start trying to do some simple calculations and starting from first principles. These are first principles, but you all know that once you master or get an idea of the first principles, using these tools like the one of Joe becomes a piece of cake, something like that. It becomes like you're playing a video game and you saw him enjoying it, okay? But you first have to master these basic principles. So that is what I've tried to put here, so that people can become comfortable, and then those tools will be very helpful for you in your practice and in any other endeavor. So I start by trying to define the minimum scope calculations that you can do from the angle of structural engineers. That's where I got a lot of material and good. Basically, I found it very useful. Then from there, I have a scenario which is already given information, but giving you that you can compute carbon for your road project. I've picked another building also. Then the last scenario is where you are doing it almost from scratch. I've tried to do something for a substructure. So again, these things are for emphasis, such that you get comfortable with the stages, okay? And here we are talking about embodied carbon. You may ask why we are talking about so much on embodied carbon. Over the years, the technology has helped us to reduce operational carbon. So when you hear people talking about energy efficiency in buildings, now we use LED lights. We use a lot of lighting with very little energy. They have really done a good job. Now, right now, the construction industry is facing a problem with embodied carbon. You guys, if there are any engineers here, they are the most rigid. They want the best steel, no scrap, the strongest, the factors of safety, they multiply times 2, times 3, but all that costs carbon, okay? Because the biggest culprits in this game is clinker, that is cement, and then steel. Because of the process of manufacturing steel, it uses a lot of energy. Then for clinker, when you're producing clinker, the chemical reactions that are involved give out a lot of carbon dioxide. Forget about the energy that is involved, but the chemical reaction. So cement clinker is one of the biggest issues. So, and all that is in the structure, okay? So if we get solutions for the structures, I'm sure that we shall have done a lot. And the other reason is that this is the carbon that is going to manifest itself within the next 30 years. Up to 2020, 2050, where the target is to have a net zero by 2050. And therefore, we need to work on it diligently. So I've not talked about these notes. The inputs is what is required when you're looking at these things. I think we saw this with Joe. I'm not going to say much. Just know that A1 to A3 are normally products from factories and all that. So there's nothing much you can do about them apart from getting them from good sources which are sustainable, okay? Then F4 and F5 are the ones on site. That there you have an input as a designer or as a construction manager or as whoever is working on site to do something about that. We shall see a bit of that. Then we have these others in B and C, but this is the framework or the table that can guide you, okay? So again, let's go to material quantities. And the advice from Joe and here is that do not be deterred from calculating embodied carbon at an early design stage because of uncertainty in material quantities. Yes, I know we have a problem as, if I talk as a quantity surveyor, we like to split hairs. And that is why probably they sometimes leave us behind at the inception of projects. We take a lot of time trying to be so accurate. But the idea here is don't overthink. okay? Use whatever you have because it will help you to get a picture, and then you can always modify your design. So try to prioritize material reduction, and there are various ways you can do that, either manually, using BIM models, using your structural analysis models, using your past experience. And last but not least, you can use a quantity surveyor's cost plan. That is if it is going to come on time, okay? And how do you report the quantities? You have to make sure that you are matching the units of measurement. Don't mix up measurements. You must know whether you are using kilograms, tons, or cubic meter, or per square meter, okay? So, and you should be comfortable or confident that the material quantity uncertainty will keep on decreasing as the project progresses. And so you have to go through a lot of iterations, as you saw what Joe was doing, okay? So for factors affecting A1 to A3 carbon, these are normally the project location. So are you in a remote area where materials are going to come so far? So here you have to look at regional or country averages. What about the manufacturing location? So you know that in Uganda, we import a lot of materials, and that's not good for us. It is better that the location of the material is closer to the site. Then lastly, thirdly, we have the material specifications. All those affect the A1 to A3 carbon. So another thing you need to know with things like steel, that there is a wide range of the carbon factor, depending on what type of steel you are using. Are you using the original from the ore from the mines, or are you using recycled material? I know that some people don't like recycled material, but you can see that if you use recycled steel, you can use 0.395 kilograms of carbon dioxide per kilogram as compared to 3.97. So there's a big range, okay? You should also seek local insights to ensure accuracy. So you have to discuss with your clients, keep talking, okay? And always start with the default values, okay? And then be specific about the sources of your information, okay? Choosing the right factor, pick a factor that matches your current understanding about the material source. Initially opt for regional or industry averages. Always be transparent, clearly state any assumptions, and revisit the carbon factors as your design progresses. Consider minimum, average, and maximum factors for materials to show potential for the range. And they still emphasize the ICE database. So ICE stands for the Inventory of Carbon and Energy. And this is an open source carbon factor database with UK, European, and global databases, okay? Offsite manufacture, they are saying that it also includes, so this A1 to A3 is mainly about things which are produced off the site, okay? What do you do when you have unknown material specifications? You use the default factors. Bear in mind that material values may change with improved production processes, so they are not cast in stone. If materials are not in the database, find suitable EPDs, but Joe said that EPDs are difficult to interpret. But the EPDs are like a certification to show that the people manufacturing that material have looked at the environmental aspects, and you're confident of where the material is coming from and its carbon emissions. So it is like it will soon become like a mark, a mark of quality in sustainability. Okay. What else can I talk about? Let's proceed. For known materials, use product-specific carbon data for more accurate carbon assessments. As your design progresses, your carbon assessments will become more certain. I said you can use EPDs because they have detailed information on environmental data. But we said that they could be difficult to interpret at the moment. These are examples of where you can find these EPDs. There are so many, but these are some of the sources. So now let's go and talk about concrete. But as I said, concrete, the biggest problem with concrete is the Portland cement. And the biggest problem with Portland cement is the clinker. Almost all cement has clinker, but right now a lot of people are trying to look for substitutes to minimize or to reduce the amount of clinker in cement. And therefore, those of you who are so rigid and staunch and conservative, you need to start looking in this direction, the engineers mainly. So there's a lot of influence that you can give us. We know we don't want to live in collapsing structures, but this is an area we need to look into, okay? So I'll leave it at that. Then here, this is a graph which shows you the amount of clinker in concrete. So and how it gets reduced as you get substitutes or other things like fly ash and all those other things that people are doing research about. So I also try to put a description of clinker and why it is unsustainable. So the reason is that during clinker production, a significant amount of carbon dioxide is emitted due to the decomposition of limestone into lime or calcium oxide, and therefore that is the process that is causing a lot of trouble. From there, we talk about steel. Steel, the biggest problem is the manufacturing process. We have two production processes. There's the basic oxygen furnace and the electric arc furnace. The basic oxygen furnace is the traditional one, and the electric arc furnace is the modern way, which uses a lot of recycled content, and that is where we're supposed to be going. Otherwise, it is mainly, we hope that this can reduce as people get other sources of better energy during the production of steel. Then the third item that I would like to talk about is timber. Of course, we have that counter issue of people fighting against cutting trees, deforestation, but from construction perspective and carbon discussions, timber is a good material because it stores carbon. If you use it in your construction, it has what we call biogenic carbon. Okay, so it stores the carbon for as long as the building is in existence, and therefore it does what we call sequestration. And as you saw in Joe's presentation, he came up with a certain figure of, I don't know whether it was 115, but because of some timber or some sequestration, it reduced to about 112, something like that. So that is the purpose of timber. The challenge we have is we don't have sustainable forests. But if we start doing that, I think we can achieve, we can contribute to reducing some of these emissions by using timber. So that's why you see people who talk about green construction, you see a lot of timber in their construction. That is the reason, because it's a store. I put a diagram that I picked from Institute of Structural Engineers from Gibbon, and it explains what timber does. So it prolongs, it postpones the emission of carbon dioxide, and therefore the timber it gives you a net zero carbon emission because of that aspect. I'm not going to talk about the science, but I hope you can be able to follow that. The calculations, I think I'm not going to do them because of time. I'm going to rush to the examples. They are simple examples. You'll forgive me for this. So we need to save some time for Q&A. So the first scenario is a road project. And there are two road projects. There are two sections of a road of about 4 kilometers. And the task is to compute the carbon emissions and present them in a format ideal for ICMS. Okay. So what we have done is I've picked out a template from ICMS and picked out the project attributes. What am I trying to do? Whole life carbon, the percentage of carbon emissions based on actual quantities. At the moment, it is 0 because it's a forecast, it's at design stage. The tool I'm using is basic Excel tool created by the developer. The standard I'm referring to, there are so many standards, but it is PAS 2080, publicly available standards. The main sources are material delivery codes, B models. So all those are, you're able to input those in the project attributes table using ICMS. And from there, This is an expanded way table of the project attributes. So this prompts you to specify all the circumstances under your design, and therefore people are able to understand the circumstances of your project. That is the purpose. But from there, you can see that this is the table of where we do the carbon under the various categories. We have acquisition, which is normally negligible, construction, renewal, and all those. And the values have been provided. And we follow this table to compute embodied carbon, then whole life carbon. So this shows the boundaries. And this is another presentation. You need to get comfortable with this presentation because it is the one which will guide you on how to allocate the carbon. And again, this one comes in as a reminder. But eventually, this is what we have as the materials or for those two projects. So we have ready-mix concrete, we have asphalt, we have piling, we have imported soils and other materials, and we add them up, and of course we have those are the total quantities. So we have so we add them up. So these are the FO carbon emissions from transport to site, and then these are the total quantities. So once you have that, then you can go on to another F5, that is the site activities. And mainly in construction, we have things like fuel, diesel, you could have some electricity, you could have water usage, you could have waste emissions and other processes. And also we add that up. From there, we go and look at the B items, B1 to B8, the user, maintenance and repair. Then we have replacement and refurbishment, operational energy, operational water, and then other processes. And then we add that up. From there, we go and look at I think this is the end of life. That is the deconstruction and demolitions, which could involve some transportation and waste processing and disposal. We add them up. After adding them up, we come to our table and input those, and therefore we are able to come up with the quantities. And we can express them as tons of carbon emissions per kilometer, and that's what I've done there. So all these are done in an Excel table without any software. So that is the first scenario. So it gives you all the quantities, and your job is to arrange them. You'll be getting them from experts like Joe, and then you can arrange them in your project. The second one is also a building project, where I've given you all the quantities. It's a municipal project, and I've concentrated, I think, on just the construction. So I have things like external works, demolitions. So once I have all this data, which has been measured by experts, I can now arrange it under ICMS in this format, as you can see, and then I can convert it into tonnage. Okay, so that's what I've done here. As long as you are conversant with the standard, everything has a code, so you just arrange it, and it becomes uniform for everyone reporting on their project, no matter how big or small. So that is the second scenario. The third one is a scenario which requires some computation, but honestly, what I've done is I picked one of the normal bills of quantities that we are so accustomed to, and I converted them to. I added additional fields for ICMS requirements, and then I used a pivot table to convert that data, and then I started doing my calculation. So that is what I can show you. So the first one is a tables for attributes and values, and then this is your normal substructure of a building. You are conversant with this. Don't mind about my incapacity to, my incompetence in coming up with the unit rates, but typically you'll have something like this for a building, for a substructure. So your task would be to convert it to measure the carbon. So all I've done is that I've created additional tables to map the BOQ items that I have traditionally onto the ICMS framework of groups and subgroups. And after I've done that, I use the pivot table to now reformat the presentation in ICM format. But when you're using a pivot table, there are some rules you have to follow. the data has to be structured. Ensure that there are no blank rows and columns. You ensure you have column headers, and you ensure you have consistent data types. Don't have eliminate merged cells, and then you introduce what we call format Excel tables, and you'll be able to maneuver. And this is what I did. This was the process of doing that after doing the other table. And eventually, I was able to classify the different work items into ICMS subgroups. And from there, I, of course, had to go into the work requirements to compute the diesel, the materials. And once I got my materials for each of those work sections, I go to the ICE database, and I picked out the standard. So I prepared this table, which looks at the production stage, A1 to A3, the transport stage, A4, and then the A5 is normally divided into two, wastage and then site activities, but I did not put anything on one of the activities because I did not have data. So it's not, as long as I'm transparent that I've not included it, it's all okay. Sometimes you don't have all the information. So I did that, and I was able to come up with these carbon emissions. And so after doing that, I compressed my table to here, and it's only for the substructure, and I came up with something like 662 tons. So that's a process, of course, that is ideal for more time. And then I did my analysis, and I found out that column bases and column wall footings were the majority. That's where the majority of the carbon was coming from, followed by the ground floor slab and ground beams. Then composite items are those items I could not define under ICMS, but under the traditional. Then I had the substructure walls and columns. So once I've done that, I can now know where I'm standing. And then during implementation, of course, the record keeping has to go on. But once you have the templates, in limited data on current practices. I'm talking about Uganda. UK looks like it's quite advanced. However, we should not avoid calculating embodied carbon due to uncertainty. By measuring and openly reporting our calculations, we can collectively reduce this uncertainty and minimize our climate impact. Another point is that using repeatable data sources is important. Databases, scientific publications, industry reports, and environmental product declarations are important to be consulted. Then the third one is that reliable and accessible data sources are critical for effective carbon assessment and reduction strategies. So you have to have some level of accuracy, then prepare. So we need to prepare ourselves for a future where carbon emissions measurements and accountability are a pre-qualification requirement in construction projects. So you know what is going on in the region. We are being accused of affecting the climate, so we have to produce evidence. So measurement becomes important of carbon. So we need to source from supply chains which are compliant with EPDs. We need to develop credible references like databases and toolkits. A lot of these are available free online, but they are mainly from not from here. So the ICMS standard provides us an opportunity to do our strategy towards moving towards net zero carbon by measuring what we are doing. And we shall need a lot of increased collaboration to address the current challenges. So that is what I have, and a lot of references here that I've consulted to put this up. Thank you for listening to my monologue.
Thank you, Tom, for that presentation. Yeah, I think it was also really interesting, slightly different perspective, but good to hear both of you. I think, yes, as you said, now there's some time for Q&A. So for people who are still here, you're all welcome to share your questions or put up your hands if you have questions that you'd like to ask yourselves. I think there were already some questions sort of from previous that had been asked a little while ago. So I guess we can probably start with that and go straight into it. I think this first question was about recycled materials and how they're used. I think, Joe, you would used an example of rammed earth. So maybe to extend on that question, it's maybe, can the user themselves create a material that can be added to the system, or if there are materials that we're looking for that are slightly more, even more friendly to the environment, like rammed earth or other earth-like materials, how can we input them and use them? So that's kind of a question.
Yeah, it's a really interesting question. So I'll deal with the easy bit first. One, it's impossible to put new materials in FCBS Carbon currently. The way it's set up means that because it's not a simple material, we create a build-up. And understanding how that build-up is calculated means just for consistency, we tend to control it. However, having said that, if people have got specific requests for materials, they tend to be sent to me. I tend to put them in for them and then just send them back. It's a much easier way to do it. So just on a kind of broader point, so things like recycled materials or materials from sites, so earth, for instance, they tend to be incredibly low carbon. So although it is worthwhile calculating them, it's only worth calculating them if you're all the way down, you've done everything else, you've saved all the carbon everywhere, then it's the time to think about it. The problem you'll probably come up against is that finding reliable data for the embodied carbon of those materials is quite tricky. Particularly if it's on from your site, you probably don't have access to the data for it. So you could probably make a bit of an estimate about, how much energy goes into extracting the material on site. I think it's quite an interesting problem. The bigger issue, and Tom covered it really well, talking about steel and concrete, these big process materials, they're huge carbon emitters. And actually, those are the ones we probably need to think about. And Tom discussed about recycling and reuse. Actually, reuse is a really simple way to do it. It's not necessarily glamorous, but it is a fantastic way to do it. So, I see there's another question in here from Felix about recycled materials and hydrated lime, byproducts of medical oxygen. Yeah, fantastic. That really fits into this kind of idea of a circular economy. So the more we can reuse these materials and give them a use and a value, the better. So they don't just end up being a kind of promoted as a kind of waste. What I would say is that waste streams are not they shouldn't be your only supply chain. They should be a kind of add-on to your supply chain. You can imagine that if, I don't quite know what the medical oxygen production line is like, but they might find a way in future to not have hydrated lime as a byproduct. And if you have a long supply chain that supports that, actually it's quite difficult. So yeah, really interesting. Tom touched on this, sorry, I'm going to go on more and more, but Tom touched on this. He talked about clinker being, the problem within concrete. Absolutely. So in the UK, we use ground glass blast furnace slag, and I know certainly in Rwanda we use volcanic ash as a replacement, is a kind of cement replacement. Really fantastic. The bits we use in the UK, this sort of, we call it GGBS. There's only a limited amount of it. So although we can replace quite a lot of cement, we can replace 75% of the cement in a concrete quite comfortably. If we take it and put it in our cement, in our concrete, it means that somebody else isn't putting it in their concrete. So although our project will reduce the carbon emissions, globally, the carbon emissions don't change. It's all used. So it's a really interesting sort of discussion on supply chain, economics, and management are super tricky.
Yeah.
I can see Tom's got a hand up as well.
Oh, and I think Tom could stay unmuted. There we go.
Yes, I wanted to have a go at Felix's question. From the research perspective, what is important is, I think this data can be got when you're doing your trial. The way you do, what do you call those things? The shop, when you're starting a site and you're doing samples and all that, you can compute the amount of effort that goes into producing that block, because probably you're going to do some compaction, maybe using some fuel. Dr. Nathan has once said that you can even measure the resources that are consumed by the personnel to make that block, like the food they eat on that day goes into that energy, but it's very little really, because it's all on site, and it's sometimes it's not worth counting, as Joe has said, but it's possible that we can do this data. We can get this data from the research, from a research point of view. As researchers, it's something that people can do actually, and try to share that data. So it's not difficult to compute from that aspect, but you can't get it from a database.
All right. Okay, thank you. I think maybe going a slightly different direction, but Tom, I'd be curious to know, I guess it seems as though like carbon and at least creating a bill of carbon is something still quite new in Uganda. I think you're saying maybe you've been doing this for the last 4 years or so. So I'm kind of curious to know about like the client base and how you encourage, I guess, the end users or the clients to use this tool, or is it something that's still sort of experimental and you're testing it on previous projects, or is it are you engaging with current clients and people who you're working with now using this tool? And I think I could extend the question to you as well, Joe, because I'm interested in knowing, I know you're using it more in the early design stage, but if you had a client with 2 different models and they're involved in that process, then are they involved and do they also have a say in the outcomes? So maybe.
I can start by giving it a try. I can say that we are not using it for commercial purposes. This is a standard that had a coalition of quantity surveying firms, mainly quantity surveying associations around the world, RSCS, for example, but also we have architects and engineers like ICE and RIBA. So they wanted to come up with a universal or a consistent way of reporting construction costs. So they came up with the first standard, which was talking about only capital costs. After using it in some countries, then they came up and they said, let's also add a standard for life cycle costs. So they went for life cycle costs. After that, then also they decided, let's start doing something to do with carbon. So they have tried to standardize the reporting and the measurement of carbon through that. So personally, it's an interest because not from the work perspective, but from academia and of course practice as professionals, because we need to have a uniformity of how we report these things. So most of the things we are doing are academic and research. And at the moment, we are doing promotion and awareness, raising awareness.
Yeah.
That's what we are trying to do at the moment, but not commercial.
Right, thank you.
Yeah, I mean interestingly, what Tom's kind of describing is what we were doing exactly 5-6 years ago. The people who were measuring it were doing it for their own interest and because they were concerned about their own impacts. What we see now is thanks to places like the RIBA, Architects Declare, and other kind of movements, and LETI, as I mentioned, there's so much more knowledge shared that people are starting to take this on. And what's quite nice is a lot of people now are starting to recognize and do it just through a normal project. It's not in our building regulations as yet. We are slowly getting there. We've been trying to get the government to do it, but I just seen our UK government has rolled back on all of its net zero pledges this morning, which is frustrating. But there you go. There you go. But I'll dodge all the rest of those questions. But it is useful. So we see lots of clients asking for it, and in fact, many of our clients now, without even talking to us, are asking for specific targets for us to hit. And the only way we can really do it is by starting at the beginning. So once we get a kind of design which is kind of nailed down, we'll start to move into something more complicated, perhaps not quite to the same level that Tom's done, but heading that way in particular. And it is really that's where you start to think about the details, changing different carpet types or something, or choosing different glass manufacturers where you can find that data.
All right. And I guess, is it, Joe, would you say that this is something you do in almost most of your projects? It's a starting point for every project, or select
Yes.
few?
Yeah, so one of the reasons we made FCBS Carbon is that we can get an embodied carbon model in about an hour of reasonable quality that we can then use to have that dialogue. So there's no real burden for us as a project team, so there's no real excuse for them not to do it anymore. It's not going to take us a week, it's an hour. And then what we're able to do is we can sit down with the client and we can show them the impact of design changes live using that tool. So we can start to say, well, actually, if it does get taller, this is the impact. Or if we change this material out, this is the impact. I mean, one of the things we are always advocating is to just use less material. You don't have to worry about the embodied carbon of material you're not using. So it's a much easier way to do it. And you don't have to worry about complicated supply chains and all that kind of thing. So again, much easier, just build less.
Okay, thank you. I think I'll ask, Ivan has a question. Ivan, you're welcome to ask your question if you...
Thanks. Yeah, thanks, Randy. Hi, Joe. I'm actually born and raised Ugandan, and I actually work in Birmingham, UK now. And my question is, basically, you like Tom was alluding to, Uganda has quite a long way to go in terms of like materials and essentially their embodied energy. So, for example, like in the UK, you can just reach out to a timber frame company and you just say, please ensure all your timber is, grown the right way. Make sure all the timber has a PEFC certificate and that type of thing. Whereas in Uganda, like Tom even said, there's no environmentally friendly forestation kind of thing. So it's so is that one of the main challenges you see in terms of carbon emissions and embodied energy on materials used in Uganda?
Yeah, it's a really interesting one. Thanks, Stephen. So there's quite a lot to unpack, but just as a kind of brief sort of thing, when you talk about timber sourcing as a good example, we can get a bit of paper and a certificate that says, here's the audit trail that says it came from this forest and it was sustainably forested, whatever that means. It's quite nice to have a bit of paper, but what I would say is nothing beats going to visit where your products are from and seeing it with your own eyes, talking to the manufacturer and providing them guidance. So quite often we use materials that don't have all of that kind of paperwork, and we're trying to use more of them. There's lots of regulatory issues and fire and all those kind of things that we have to be aware of. But actually sitting down with a supplier for a couple of days and working out, okay, what's your waste stream like? How does this work? You've thought about this kind of forestry, and building up that kind of relationship and having that kind of open dialogue. That's probably the first thing to do. We are doing a bit of embodied carbon work in Rwanda at the minute with Mass Design and the University of Rwanda. So Alex Ndubwami, I know some of you might know him, working with them to put the framework there. I mean, it's been really good, actually. We managed to get some local EPDs produced. We managed to get a bit of a framework going. But actually, just the more you advocate for it, the more you talk about it, the more you encourage people to do it. And it's all about encouragement. It's not about saying what people are doing are bad. It's saying you could do it better, and here's how you could do it, being constructive. And I think that's the kind of process we've been going through for the past 5 years in the UK, and we are getting there. We from having something like 2 or 3 EPDs for UK products, we've got, I think it's 14,000 in the UK or something like that. So it's really improving. So I think that's the process. Tom hit on a really important point that the carbon emissions per capita in Uganda are very low compared to most, certainly the UK are at 5 or 6 or something tons per person, which is fantastic. The question now is how do you maintain that kind of level rather than kind of repeating our mistakes? That's the key thing. So yeah, hopefully that answers some of it, even.
Yeah, it does. Thanks for that. Just one last quick question on recycled materials, because I think in Tom's presentation again he talked about recycled steel and trying to encourage most of the structural engineers to specify recycled steel, and he actually gave an example of new steel would have embodied energy of 3 point something, and he said if it was recycled it would go to 0.3. So is that a generic formula you use for recycled material, or does it vary dependent on the material?
I'll quickly answer, and I'm sure Tom might have a better response as well. No, it's material specific. Steel, part of the difficulty in making steel is the extraction of the original ore to make iron. And then there's kind of blast furnaces. What you'll find is if you've got recycled steel, you just need to melt it, and that's much lower carbon. Some materials, it's much lower carbon. Glass, again, similar processes, aluminium, but it doesn't necessarily work for all materials. So unfortunately there's not a simple formula you can just kind of apply. But yeah, very material specific.
And is there any risk in, so are you physically saying like a steel beam, or when you said melt it down, you're saying melt it down and essentially manufacture it again, or what? When you said melt it down, what are you, yeah.
So just for sort of clarity, no, it's good. It's a really important point. So when we say recycled, what we mean is that it goes through a process and comes back as effectively a new product. So it'll go into a manufacturing process. So steel is a really good one. So it'll get melted down, and it'll turn back into a brand new steel beam. You wouldn't know it's any different. It might have some different markings. The other way of looking at it is reuse. So that's where you take a steel beam out of a building and then you reuse it directly in another building. And I think that's something we're doing more of in the UK, but it's very difficult to say how well that beam's going to perform, because it could have been a building for 60 years. What was the quality of steel? So there's lots of processes getting there. So there's a bit of difference between reuse and recycle.
Yep. Okay.
Thank you. I would like to add on for Ivan. I think, of course, as a QS, I have no authority to talk about the strength of materials. I might be arrested, but I found a lot of good information from the Institution of Structural Engineers from the UK. They are really promoting substitutes and all these other things, and they back them up with the research and evidence. And therefore, if you're a structural engineer, you can start from there, and you see their arguments and discussions, and then you see whether you can borrow some of those ideas. Thank you.
Thank you.
So I think there's a question from Nathan. I might unmute you to ask. There we go. If you're still there, I don't know.
Can you hear me?
Yes, we can hear you. Yeah.
Thank you, Randy. Thank you, Joe. Thank you, Tom. I'm Nathan from Makerere University. I work with Tom. Tom is my PhD student. Tom, thank you for the presentation. Mine is just a couple of comments here and there. It's quite interesting to see such useful presentations about the current issues about carbon, and especially from the developing country here. The biggest challenge, of course, had to do, as Joe has said, and Tom, the databases, the carbon sources is a challenge. Like at the department, we are trying to profile a few materials that are used, trying to calculate their, for instance, the carbon emission, embodied carbon of a brick manufactured in Uganda, embodied carbon of cement. But of course, it's quite resource intensive. But hopefully, after some time, we'll have some small database which we can gradually compare with in other places, and maybe to be a little bit of representative from the from the sub-Saharan Africa or something like that. The other is just maybe just to Joe about the tools. There is so many tools really around, and it's good to see your presentation of the tool. Maybe just to check. Of course, there is quantification, which is very good. Then when we get the quantities, then we need to make that decision as you presented. Where are the hotspots? Is it in substructure? Is it in superstructure? And the question now comes, what are the options? What can I do? So in your experience, like, to what extent can we have these tools really help us to make that decision? For instance, like, okay, if you have the biggest percentage of embodied carbon in this section, these are the options you can take, especially that we have a number of majority of people who are not much into the area. And then right now you need to first read a lot into materials and carbon and everything to be able to make those cautious decisions. So how do you see this being developed from the tools maybe to become a little bit more intelligent, and they're able to give you the quantities, and they're able on the sidelines to give you the options. Now, whether the options are there or alternatives, that's another question. So what's your opinion on that? Thank you.
Excellent. Thanks, Nathan. That's a really interesting question. So yeah, one of the reasons we made FCBS Carbon is to help people. I think I said this about helping people reduce their carbon emissions. So within the tool, it's not just a simple long list of materials. What we have are a list of common materials that go for it. So if we look at beams, we'll have currently we've got a couple of different concrete mixes. We've got steel. I think we've got iron, because occasionally we have an iron beam in the UK, fairly rare, but we do. We've got glulam timber beams. I think we've got a roundwood beam at the minute. There's a few others. But what you can do is quickly, just because it's just a drop-down menu, you can just run through them and say, which one's the lowest one, and you can kind of iterate through it. So I think that's one thing. What I would say is, what we're seeing in the UK is low carbon materials are becoming a very desirable thing to have. So if you've got a choice between two manufacturers, the low carbon one will cost certainly more, and probably more likely quite a bit more, because everybody's asking for low carbon materials. So the key thing is, rather than relying on which material is a better material, ask if you need to have that bit of your building in there. Now, some things you can't get away from. You're probably going to need a structure of some sort, but actually, can you reduce how much structure you use? And actually, that can be a really fun discussion to have with your structural engineer about. Okay, and again, Tom hinted at this. He said about safety factors. Do you need all those safety factors? Build to the codes. Don't build over the codes. So really start to think about those kind of interrogations first. If you build less, you don't have to worry about what that materiality is. It becomes far less important. But yeah, so within the tool, there are substitute materials. They should all work roughly the same kind of way. There's factors that all account for them. So there's definitely a bit of shopping and changing you can do. Again, FCBS Carbon's not an end answer. It's about getting the process more efficient and getting carbon part of that discussion. Hopefully that helps. Oh, Randy, I think you're on mute.
Sorry, thank you. Yeah, thank you for your question, Nathan. I think it's been answered. I'd say maybe one more question if we have. I could ask the question. There's a question in the meeting chat about kind of emissions that come from other areas of construction. So, for example, excavation and the sort. And then maybe the question is if it's integrated within the material and how the material is used, or if this is a completely separate item that is not accounted for. I think to both Tom and Joe.
Yeah, I'll let Tom answer. I think but what I would say, so in FCBS Carbon, we do account for some of that, but it's very basic. We just use simple percentage uplifts. So yeah, lots going on in it. Tom might be able to give a better figure about how he kind of calculated or looked at it. But it tends to be far. Sorry to put you on the spot, Tom, but it tends to be less carbon intensive than some of the bits, for instance. And I think that's quite an interesting learning.
In my experience, it was a challenge, but it came down to the technology you are using. If it's a house, a small structure where you are using manual labor to do the excavation, it's almost negligible because you are just using hand tools. But when you bring in machines like excavators and backhoes, the biggest component was the diesel that I found. How much diesel are you going to consume? So it turns out that becomes the biggest component. So if you have an electrical excavator, which is not yet in Uganda, again, it will become almost negligible because probably you'll be using clean energy, or a solar-powered excavator. Yeah. It will become almost zero. But as long as we are using fossils like diesel, and especially on civil engineering works, a lot of almost, I don't know, maybe 50% of the money goes in diesel. So it's a lot of emissions that go on in excavation work, and therefore you need to track them and measure the consumption, and that is going on actually on our sites. We measure how much we've consumed and all that. So it comes down to the consumption of things like diesel for such works. Thank you.
Yeah. Okay. So still a point of something to still measure and a point of question. Thank you. I think I might just ask if the two of you have any final remarks or things you'd like to say, closing remarks, so that we can close this session. And then if there are any other questions, I'm sure they can come later and we can continue to answer them in the future. So I'll hand over to maybe, I don't know, Joe first, and then Tom, if you'd like to share anything before we end.
Yeah, two things, I suppose, off the top of my head. One, thank you so much for putting on these series of events and talks. I think it's fantastic that this discussion is going on. What I would say is don't be shy or scared of getting stuck into embodied carbon. Pick a building element that's of interest to you and just calculate that and do it by hand. Once you understand all the kind of ins and outs of it, use the RICS guide that I mentioned and Tom mentioned. That will give you most of the kind of carbon factors. That'll give you most of the guidance. Have a crack at it for a bit. Maybe it's a bit of wall, maybe it's a window, maybe it's a bit of structure or something. Maybe it's a bit of roof. Have a go, see if you can find all the data. And then once you start to understand it, then start to look at the tools and really get going with it, because you'll understand what's correct and not correct in the tools. But just to finally end, but thanks for inviting me along, and do, if there's questions, send them on. I'd love to hear what's going on in the world. Fantastic. Thank you.
Thank you.
Like Joe, I'm also very happy to be here, and I am grateful for the invitation that you actually thought about such a topic. You contacted us around a month ago, and we discussed with your team, and I told them that I work with Dr. Nathan, but you decided to zero on me. I wanted to shy away, but I said, no, let me get it on. Since I'm trying to practice and trying to create awareness and promotion, and the more the players, the better, and we will be able to probably do sustainable construction as time goes on and create awareness and stop scaring people also, because sometimes when these things are in the hands of politicians, sometimes they blow them out of proportion, especially the issue of timber. Timber is a good product if you nurture it well. You use silviculture, encourage people to manage forests, but don't scare people that you're going to shoot them because they are cutting trees. So we need to be aware of the science, and it will help us move forward. Thank you.
Yeah, thank you. Thank you for that. And I guess thank you both for your, I guess, commitment to the topic and being willing to encourage us all to give it a go. Yes, it's been really interesting. And I think, thank you to speakers and the audience as well for joining us. There are a few people who regularly join us, so thank you for that. And then also just housekeeping about local talks, that I think I'd said in the beginning, but we have one every third month. So the next one will be in December, the third Wednesday of December. So I think we're already thinking about the topic, but we'd love more feedback about local talks, how you find this session in particular, previous sessions, and ideas for future sessions, because I think the purpose is to include people who are interested in this topic in the decisions we make. So yeah, we'd love to hear more from you. I think that's everything. I'll close this session. Thank you for joining.